I will have 79.1 equals 82.3 times e to negative 0.004 t. Okay. Now, this is what we studied log equations, log and exponential equations in the previous section. So now we have to remember what to do here, step by step.
Natural log?
Not yet. Not before I get rid of this. Because if I apply natural log, this will become a product, and then I have a sum of two terms. So it is recommended to get rid of this. Divide by, 82.3, 82.3. So then e to negative 0.004 t is this number. Don't calculate. Now we have to apply natural log. Perfect. Yes. So we apply natural log to the left-hand side. And we get negative 0.004 t. Remember, I should write times natural log e, but why don't I write natural log e?
Because it equals 1.
Very good. Equals natural log 79.1 over 82.3. And now, of course, I divide both sides by this number. I don't know if you can see this one, so good. So that's our final question here. And we can look at one more concept and then we can put this chapter to rest, unless you have questions. I'm hoping you have finished everything, including 4.4 by now, please. 82.3, close the parenthesis, and then divide. Careful with parentheses. You don't have to put a negative, but you have to remember it's there. Or you put parentheses, negative 0.004, and close the parenthesis. And we have to I was expecting, oh yeah, it's 10. Okay, yeah, of course. Okay, so t approximately 9.91 years. Yes, I was expecting to see roughly 10, but that's what it is, roughly 10. Not exactly, it's not exactly the same. So in approximately 9.91 years since 2010, which is roughly at the end of 2019, the population of Germany should be in the vicinity of 79.1, according to the model. Okay, so let's look now at an exponential growth model, and then I would like to talk about half-life of a radioactive substance. I should have not closed the book. I should have put a bookmark in there, so okay, I got it. Okay, so let's look at problem 8. On page 529. They're telling us that in the year 2000, the population of the Palestinians in the West Bank, Gaza Strip, and East Jerusalem was approximately 3.2 million. And by 2050, it is projected to grow to 12 million. Use the exponential growth model, A of t equals A0 e to kt, in which t is the number of years after 2000. So t equals 0 represents the year 2000, we know that. To find the exponential growth function that models the data. And then in part B, in which year will the Palestinian population be 9 million? That's for part B. In part A, they want us to determine this, which I don't have, sort of, and this. So we want to determine the initial population, and we want to determine the growth rate. And that will completely define the model, because A is the y value, or the function. T is the independent variable. And what we don't have are these two constants yet. Okay. But what am I given here? When I'm told in the year 2000, I get this number. In the year 2050, I get this number. And X represents, T represents the number of years after 2000. Then I know that I'm given two ordered pairs. Can anyone give us those two ordered pairs so we can write them correctly? What will be the first ordered pair that you can think of? I hope you will be thinking of 0, 3.2. And what is the second order pair that we should write? Anyone?
Would it be 0 and 12?
So it's going to be 50 years later. So 50, indeed 12.
12.
Is that better? Is that clear?
Yeah.
Perfect. So I write the model one more time. And let's see how I plug in the point. When t is 0, the function value is 3.2. When t is 0, the function value is 3.2. So then 3.2 equals A0, e to k multiplied by 0. But k times 0 is 0, e to 0 is 1. So as we kind of knew, right, from the very beginning, the initial population is 3.2. I will plug it in. It will replace 3.2. I replace A0 by 3.2. So for now, the model is this. E to kt. I am given another point. The other point is 50, 12. Can anyone give us an equation that you get when you plug in 50, 12?
So you should get 12 equals
3.2
E
to k.
K 50.
Excellent. So now when t is 50, a of t is 12. Excellent. Good. So now we have to, like before, we have to first divide by 3.2, but not actually perform the operation. And yes, we have to use the inverse function. What would be the inverse function of e to the x that I have to apply to both sides?
Natural log.
Excellent. So natural log of 12 divided by 3.2. I bring down 50k. I should write times natural log e, but again, we know natural log e is
1.
perfect. Excellent. Great job. So finally, k is whatever over 50. And now when we determine k, we have the entire model. No secrets whatsoever. So natural log, in parentheses, don't forget for parentheses for inside the natural log. It pops up with the left parenthesis anyway. Don't forget to close it. And divide by 50. And we get 0.0 for radioactive decay rate or exponential growth, please use 4 decimal digits. The more we use, the better off we are, because it can drastically change. If you put 1 more digit, you'll see the difference without the 5th digit and with 5th digit could be substantial. Okay, so finally we have the entire model. So it's 3.2 e to 0.0264 t. Done. This is the model. The initial value is known. The growth rate is known. The dependent variable is this. The independent variable is that. This is it. This is our function. Now they want us to determine when will the population reach 9 million. Like before, this is our part B. 9 million equals 3.2 e to 0.0264 t. Nothing different. I divide by 3.2. And like before, a minute ago, we are applying natural log to both sides. So then we have 0.0264 t equals natural log 9 over 3.2. So therefore t equals all this over this. I'm going to perform this calculation in 2 ways. I'm going to use, instead of the approximation, I'm going to use this entire answer. And then I'm going to redo the calculation with our approximation with only 4 decimal digits. So I have natural log of 9 divided by 3.2, and then I divide by the previous answer. And with the previous answer, the entire answer, nothing truncated, I got that t is approximately 39.117. Now I'm going to redo everything, this calculation, divided by 0.0264. I'm just curious to see. The difference is at the second, not the 10th, but the 100th. So it's, for this situation, it's not such a big deal. So this is years. And we were talking about since the year 2000. That was our initial value, initial moment, so t equals 0 in 2000. So this is in 2039 approximately. Okay. Let's look this time at a situation with the exponential decay. Any questions for me before we look at the exponential decay? We looked at one, where was the population of Germany, but this time I would like to look at something with radioactive decay and half-life. Yes, problem 30. So this is 30 on page 530. I will not copy the problem before I explain what this means. So let's suppose in an experiment or in a lab we have the mass of 100 grams of a substance. And let's suppose that what is called half-life is, let's say, 10 days. I'm making all this up. Which means we start with 100 grams today. Today, 100 milligrams or 100 grams. 10 days later, we have 50. 10 more days later, we have 25. 10 more days later, we have 12.5, and so on and so forth. So this is what is called the half-life of this substance that we are talking about here. It diminishes, it reduces, or it makes 50% of the mass disappear in 10 days. So even if we don't touch it, I don't know if it's kept in vacuum but if it's in plain atmosphere, from 100 grams in 10 days, you will go back to your lab and you'll find only 50. 10 days later, you'll come back and you only have 25. So this is what we call the radioactive decay. It reduces its mass in time. And this is the time that it halves the initial mass, halves the initial mass, halves the initial mass. So then the half-life is 10 days. So let's look at a problem like that with a half-life. Any questions? Okay. So problem 30 on 530 says the half-life of aspirin in your bloodstream is 12 hours. Okay. It's a substance. It decreases its mass according to the exponential decay model. But every 12 hours, if I take 100 grams now, not in 10 days, but 12 hours later, I have 50 in my system. 12 more hours later, I have 25 in my system, and so on and so forth, in my bloodstream. So let's see what they want. They say, how long will it take for a sample of the substance to decay, time to decay to 70% of the original amount? Okay, so it doesn't give us anything else. Let me put something in there and put it away. Okay, so we don't know, I can't tell you how much I took. I took an amount, let's say that is A0, unknown. I don't remember how many I took. Maybe I took 1, maybe I took 2. I don't even remember what is the concentration. So I don't know how much I took. But because it decreases its mass in time, it will definitely follow this, and it will be given to you. This is the radioactive decay. So I do not have A0, but I took A0, but 12 hours later I have A0 over 2. Another 12 hours later I have this amount, A0 over 2, which is A0 over 4, and so on and so forth. So here is a point that we just created. 12 hours, A0 over 2. I would like us to put this in the model. So I know I took A0. I don't know how much, I don't care. But I know that 12 hours later, in my bloodstream, I will have this amount divided by 2. 12 more hours later, I will have this amount divided by 2. 12 more hours later, I will have this amount divided by 2, and so on and so forth. I only need 1 point. I don't need to continue. This is good enough. So I have that 12 hours later, I have this amount. You can say, what about this point? At 0, I have A0. That's another point. But I would like, yes?
Question. Could you just, could you use like 100% and 50%?
Yes, you could. Because the answer will only be 1/2 anyway.
Okay.
No matter what you do. Yes. But normally we don't put percentages in the equation, but it will not make any difference in this case. So, can anyone help put this point in the equation? This is A0 over 2 when t is 12. How should I write this? A0 over 2 equals A0 e to negative k multiplied by 12. I will divide both sides by A0. I don't have it, I don't care what it is anyway. So then the left hand side is 0.5, the right hand side is e to negative 12k. And I'm back to the same procedure like 5 minutes ago. Apply natural log. So natural log 0.5 equals negative 12k, and I found k. So then k equals, with the calculator, natural log 0.5. Don't forget to put parentheses around the denominator. And I got 0.05776. I used 5 decimals in this case. So now then I know that a of t equals a0, which we don't care about, negative 0.05776t. This is just the model. Remember what the problem is asking us. Find the time for the amount that I took of aspirin to decay not to 50% but to 70% of the original amount. So from 100% down to 70%. So the time for 0.7 times A0. %70 of the original amount. I just have to put this point in, or just simply say A of t is this, and that's good enough. 0.7 A0 equals A0 e to negative 0.05776t. Of course, that will go away. Of course, as you see the pattern now, all these problems are identical. So natural log of 0.7 equals negative 0.05776t, and then t equals this over this. So natural log of 0.7 divided by the previous answer. And I did something. Okay, I want to put in parentheses minus the previous answer. 6.17. What does 6.17 represent? Measurement unit. What does it mean?
Is the hours?
Yes, indeed. It is number of hours. I take the medication, the aspirin right now. In 6 hours, it goes from 100% down to 70% of what I took in 6 hours. Any questions? Questions? Okay. Can we consider